So the tangent line agrees with the value of the point. T1 of f, T1 of a equals f of a. And T1 prime of a equals f prime of a. In other words, this line agrees at the point and the slope agrees. Okay? But there's nothing special about the function I'm using, and there's nothing special about the point I'm using. If you said, Ted, I don't really want the best tangent line. I want the best quadratic. I want the best parabola that fits. Call it T2, 2 for the degree, right? Second degree. T1 for first degree, T2 for second degree. Then there is one, and what's going to happen is T2a is going to be f of a, and the derivative is going to agree. But I get one more bonus. I get the second derivative is going to agree also. In other words, the curvature at this exact point is exactly the same. You can do that for 3 or 4 or 5. You give me a function that's got 10 derivatives, and give me a point on the function, and I can find you a 10th degree polynomial. 10th degree could have lots of bumps, right? Like 9. And that sucker will be so close to this right there. Why is it close? Because it agrees at the point. It agrees in the first derivative, the second derivative, the third derivative, the fourth derivative, the fifth, sixth, seventh, eighth, and 9 derivatives it agrees. That would be t to the 10th. It would be a 10th degree polynomial. So it would look like a1 x to the 10th plus a2 x to the 9th plus a3 x to the 8 plus dot 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 all the way down to a10. 10th degree polynomial, and it agrees with that function at that point, and it agrees in the first, second, third, all the way to 9th derivative. With me on the concept?
Yes, sir.
Okay, so now what I want to do in the last 5 minutes, I want to show you that I really can find the second degree. In other words, I don't want to just claim I can, I want to actually do it. Okay. I won't try to do it with one hand microphone. I got to get that messed up. Alright, so I want a polynomial t2 of x. So it's going to be ax squared plus bx plus c, right? Find a, b, and c. And I want t2 of 1 to be f of 1, t2 prime of 1 to be f prime of 1, and t2 double prime of 1 to be f double prime of 1. Okay? So I need f prime, and f double prime, right? Well, we have f prime over here. So f of x was 1 over x. So f prime of x was negative 1 over x squared. So f double prime of x was negative x to negative 2, so negative 2 over x cubed. T1 of x is ax squared plus bx plus c. T1, that's 2. T2 prime of x is 2ax plus b. T2 double prime of x is 2a. How am I doing so far in my derivatives? Andrew says they're good. Raven says they're good. Rachel's nodding off. Okay, so what did I want? I wanted this. We know what f of 1 is, right? F of 1 is 1. F prime of 1 we figured out was negative 1. F double prime of 1 is positive 2. Right? So what do I need? So what do these 3 equations tell me that I want? What's another way to write that first equation? What? Right? Except that you know that x that we're interested in is 1, right? So a plus b plus c, equals 1, and the second one, if I put the 1 into this one, I get 2a plus b equals -1 when I put 1 into this one. And 2a equals 2. Right? That's same thing, right? Good? That's easy, right? What's a got to be? 1. So now I'm just solving backwards. A's got to be 1. What's b got to be?
B's got to be -1.
2 plus b is -1. And then 1 minus 3 plus c has to be 1. And so c has to be 3. So my T2 of x needs to be ax squared plus bx plus c. Now if you put 1 into it, let's check. If I put 1 into it, I get 1 minus 3, -2 plus 3, that's 1. I mean, you can check each derivative, right, to see that it agreed with that, to see that we didn't do any stupid algebra mistakes. But I never make stupid algebra mistakes when y'all are watching, because you always catch them.
Why, like finding like a 10th degree why?
Say it again?
Like why find it? Like
Why find this? Because, again, you're programming a calculator and you need a sin x button. You've got to tell the computer chip, when this idiot punches the sine of 30 degrees, you've got to tell the chip what to do in order to spit out a number, right? But the chip doesn't know what sine is. But if you could write sine of x as 5x to the 10th minus 3x to the 9th plus 2x squared, it's not quite there. But if you could write it as a polynomial, then chips know how to add, subtract, multiply, and divide, right? That's basically all a computer chip does. So if you could write it as a series or as a polynomial, then when they punch the sine button, you could tell the chip, look, this is the equation I want you to compute. And the chip could add, subtract, multiply, and divide. You don't have to think about it when you hit the sine button, but when you hit the sine button, it computes a Taylor polynomial. It computes a polynomial just like this for the sine function.
so, but calculators do know how to do it with the sine function, but what it's actually doing is using the polynomial.
What it's actually doing when you punch the sine is it's computing an approximation to the function using a polynomial.
So you're teaching this conversion.
So what we're learning is how, so the moral of the lesson is, how do you approximate functions, any function you want, using polynomials. In Calc 1, you learned how to approximate a function using a line. But your calculator, if you use linear approximations for sine, you're going to be very disappointed the first time you launch a missile. Not going to go the right direction, because that's not accurate enough. If you used a quadratic, it wouldn't be accurate enough. But if you use a 10th or a 100th degree polynomial for sine, it's close enough. Because that's what we're going to learn is how to write, like I first started, how to write functions. Instead of writing sine x, we're going to write it as an infinite sum, which is just an infinite polynomial. If I write x to the 2n, n equals 0 to infinity, that's just x to the 0 plus x squared plus x cubed up 4th plus x to the 8th. That's just an infinite polynomial, right? Series, the reason we learned series is so we could write infinite functions. Functions, infinite polynomials to approximate functions. That's the moral. Stay off the street. I will see you